Area between two curves. There are a number of different methods for using integration to find the area between two curves, but the methods share a number of common features. Number 1. Start by finding the points of intersection of the two curves. This is essential as it gives the limits of integration. It also provides us with useful information for drawing the curves. Number 2. If we are not supplied with a graph, draw a rough sketch of the two curves. This is because it is important to see their relative positions. We use whatever information we can get, for example, points on the curve, knowledge of the shape of a quadratic curve, maximum and minimum points, to help draw the two curves on the same graph. Addition and subtraction of areas. To find the area between two curves, we can calculate the area between each curve and the x-axis or the y-axis, being careful with the positions of the curves relative to the axes. Then we can calculate the required area by addition or subtraction. Don't forget that we are allowed to calculate regular areas, for example rectangles, triangles, by using well-known formulae for these areas. So the area of a rectangle is length times width. The area of a triangle is half times base times height. Number 1. Find the area bounded by the curves y equals x squared plus 2 and y equals 4 minus x squared. To find the points of intersection of the curves, we equate the y expressions. So we let x squared plus 2 equal to 4 minus x squared. So x squared plus 2 equals 4 minus x squared, and then we solve for x. So we get 2x squared equals 2, so x squared equals 1, so x equals plus or minus 1. So when x is equal to plus or minus 1, y is equal to plus or minus 1 squared plus 1, which is 3. Or y is equal to 4 minus plus or minus 1 squared, which again is equal to 3. Thus, the points of intersection are minus 1, 3 and 1, 3. So minus 1, 3 and 1, 3. The curves are quadratic. Y equals x squared plus 2 is U-shaped, while y equals 4 minus x squared is N-shaped. So U-shaped, N-shaped. Let A1 be the area between y equals 4 minus x squared and the x-axis for x values between minus 1 and 1. So here's our x-axis, here's our y-axis, here's minus 1 on our x-axis, 1 on our x-axis. Here's our curve, and this yellow shaded part is the area between the curve and the x-axis, between minus 1 and 1 on the x-axis. So A1 equals the integral of y dx between 1 and minus 1, which is equal to the integral of 4 minus x squared dx between the limits 1 and minus 1. So the integral of 4 is 4x, the integral of minus x squared is minus a third x cubed. So now we sub our upper limit, which is 1, into each of the x's. We get 4 minus a third, then we have a minus. Then we sub our lower limit into each of the x's, and we get minus 4 plus a third, and that gives us 22 over 3. So this yellow area here is 22 over 3. We're going to let A2 be the area between y equals x squared plus 2 and the x-axis for x values between minus 1 and 1. So this yellow area here. So this curve here is y equals x squared plus 2. So, and this is our x-axis. So between minus 1 and 1 on our x-axis, this yellow shape here, this yellow shaded part, is the area between y equals x squared plus 2 and the x-axis for x values between minus 1 and 1. So A2 is going to be equal to the integral of y dx between 1 and minus 1, which is equal to the integral of x squared plus 2 dx between 1 and minus 1. So we take our upper limit, which is 1, sub it into our x values, so we get a third plus 2, then we have a minus. Then we sub our lower limit, which is minus 1, into our x values, so we have minus a third minus 2, and that gives us 14 over 3. So this area here in yellow is 14 over 3. So since we're interested in the area between the two curves. It's this yellow part here. So we already worked out this entire area. That was A1, which was 22 over 3. Then we worked out this area, which was A2, which is 14 over 3. So to get the area in between them, we just subtract, and we're left with 8 over 3. Vertical and horizontal translation of curves. Finding the area between two curves can sometimes be simplified by translating both curves vertically or horizontally. This is especially true when finding the area between a curve and a horizontal or a vertical line. Then we can translate both curves vertically or horizontally so that the horizontal line becomes the x-axis or the vertical line becomes the y-axis. Example 2 shows how this is done. So find the area bounded by the curve y equals minus x squared plus 5x minus 1 and the line y equals 3. So when we hear area, we want to think integrate. So here's our x-axis, here's our y-axis. This blue curve is the curve given in the question, y equals minus x squared plus 5x minus 1, and this yellow horizontal line is the line y equals 3. Now, as you can see from the graph, if we were to move our curve down by 3 units, the line y equals 3 would actually become the x-axis. So we start by finding the points of intersection. So what we do is we equate the curve and the line. We want to find these points here, these points of intersection between the curve and the line. So we equate the curve and the line. So y equals minus x squared plus 5x minus 1 and y equals 3, so we let them equal. And then we solve for x. So we get minus x squared plus 5x minus 4 equals 0. So positive x squared minus 5 plus 4 is equal to 0. So factorising x minus 1 multiplied by x minus 4 is equal to 0. And solving for x, x equals 1 and x equals 4. So 1 on our x-axis and 4 on our x-axis are the points of intersection. The points of intersection are therefore 1, 3 and 4, 3. So 1, 3 and 4, 3. So method 1 to work this out. So as I said in the previous slide, one way of doing it is that we translate our graph 3 units down, but we're going to have a look at a different method first of all. The area between the curve y equals minus x squared plus 5x minus 1 and the line y equals 3 is the area between the curve and the x-axis for x values between 1 and 4 minus the area of the rectangle with the vertices or corners 1, 0, 4, 0, 4, 3 and 1, 3. So here we can see we have our rectangle in yellow. So the vertice or the corner 1, 0 is here. The next one 4, 0 is here. Then we have 4, 3, which is here, and 1, 3, which is here. So they're the 4 corners of our rectangle. And it's actually a square, because the difference between 1 and 4 is 3 units, and the difference between 0 and 3 is 3 units. But we can call it a rectangle for the sake of the question. So if we got the area below our curve, between our curve and the x-axis, between 1 and 4, and then we subtracted this yellow rectangle from it, we would be left with what we're looking for, which is this purple area up here. So the area is equal to the integral of minus x squared plus 5x minus 1 dx between the limits 1 and 4 minus 3 times 3, which is our rectangle, or in this case it's actually a square. So we're going to integrate minus x squared plus 5x minus 1, and we get minus a third x cubed plus 5x squared minus x. And that's between the limits 1 and 4, and then we're going to subtract to 9, because 3 by 3 is 9. So subbing our upper limit 4 in place of our x values, we get this. Then we have a minus. Then subbing in our lower limit, which is 1, in place of our x values, we get this. And then we minus the 9. And we're left with 9 over 2. So the area we're looking for is 9 over 2. So method 2, if we translate the line y equals 3 vertically by minus 3 units, this line is mapped to the x-axis. So if we were to move our curve down by 3 units, we would actually have this line y equals 3 matching up with the x-axis. So we need to move it down 3 units. We need to find the image of the curve under the same vertical translation. Under the vertical translation of -3, the image of the curve is y equals minus x squared plus 5x minus 1 minus 3, which gives us y equals minus x squared plus 5x minus 4. So now this is the curve, y equals minus x squared plus 5x minus 4. Then the area is, so our new curve, so minus x squared plus 5x minus 4 dx between the limits 1 and 4. So we integrate, minus x squared becomes minus a third x cubed, plus 5x becomes plus 5 over 2x squared, and minus 4 becomes minus 4x. Now we sub in 4, which is our upper limit, in place of all our x's, and we get this. Then we have a minus. Then we sub in 1 in place of our x's, and again we end up with 9 over 2, which is the same as we got in the last slide. So the area, the purple area, is 9 over 2. Vertical strip method. Sometimes the region whose area has to be found must be divided into many sub-regions in order to use integration. In some such cases, a more convenient approach exists. For example, suppose we want to find the shaded area shown below. So this shaded area here. So here we have a green line, straight line, and we have a curve. And we want to find this shaded area between the line and the curve. In theory, we can divide this region up into a very large number of narrow vertical strips. So there's an example of one of them in yellow. And sum or add the areas of all these strips to find the shaded area. So if we broke this shaded area down into many, many vertical strips like this yellow one, and we got the area of each of them and we added them together, we would get the total area of the shaded part. Consider the typical strip shown, so this yellow strip. Its width is dx. So this width here is dx. If y1 is the lower curve, so y1 is the green curve, or straight line really, and y2 is the upper curve, so our blue curve, then the height of the strip is y2 minus y1. So y2 minus y1, that would be the height of the strip. Taking the strip to be approximately rectangular. Then, as the number of strips tends to infinity, so as the number of strips gets bigger and bigger and bigger and bigger, the area is equal to the sum of y2 minus y1 dx, which is equal to the integral of y2 minus y1 dx between the limits a and b. In practice, we substitute y2 and y1 in terms of x before integrating. The limits of integration a and b are from leftmost strip to the rightmost strip. So that's point A, the leftmost strip, so the strip furthest to the left, and B, the rightmost strip, or the strip furthest to the right. This method has a number of advantages for this type of question. We don't have to divide the area up into pieces. It doesn't matter whether the area is above or below the x-axis. If it is more convenient, we can draw a horizontal line or strip and use the area equal to the integral of x2 minus x1 dy between the limits d and c, where x2 is on the right and x1 is on the left, and c and d are the limits on the y-axis. However, there are a couple of points to remember. We must still start by finding the points of intersection, or at least the relevant coordinate of each, and draw a rough sketch. For a vertical line or strip, the region must have one curve for its entire upper boundary and a single different curve for its entire lower boundary. So the area between two curves, the strip method. The area of the region bounded below by the curve y1 equals f of x and bounded above by the curve y2 equals g of x for x values between a and b is the area equal to the integral of y2 minus y1 dx between the limits a and b, which is equal to the integral of g of x minus f of x dx between the limits a and b. Find the area of the enclosed region bounded by the curve y equals x squared minus 6 and the line y equals x. So when we think area, we want to think integrate. So this is the curve y equals x squared minus 6, and this is the straight line y equals x. The curve y equals x squared minus 6 is a U-shaped quadratic curve with a local minimum of 0, minus 6. So here is our minimum point, 0, minus 6. This can be verified by a table of values, translating the curve y equals x squared vertically by minus 6 or by using differentiation. The line y equals x contains the points 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, etc. and also minus 1, minus 1, minus 2, minus 2, minus 3, minus 3, minus 4, minus 4, and so on. To find the points of intersection, we equate the line and the curve. So the curve is y equals x squared minus 6, the line is y equals x, so we equate them. So we have x squared minus 6 equals x. So we get x squared minus x minus 6 equals 0. Factorising, we get x minus 3 times x plus 2. And solving, we get x equals 3 and x equals minus 2. So if x is equal to 3, then y is equal to 3. So one of our points is 3, 3, one of our points of intersection. And if x equals minus 2, then y also equals minus 2. So our other point of intersection is minus 2, minus 2. So here we have our 2 points of intersection, 3, 3, and minus 2, minus 2. Now consider the vertical strip shown of width dx. So here we have our vertical strip. It's a very, very narrow vertical strip, and it has a width of dx. So as y equals x is the upper curve, y2 is equal to x. So here's the line y equals x, and we can see it's the upper curve, so it's above the shaded part we're looking for, which is this. Then y2 is equal to x. And as y equals x squared minus 6 is the lower curve, so it's the lower curve, it's below the area that we're looking for, y1 is equal to x squared minus 6. So y1 is x squared minus 6. So the area is equal to the integral of y2 minus 1 dx between the limits minus 2 and 3, which is equal to the integral of x, because y2 is equal to x, minus x squared minus 6, because y1 is equal to x squared minus 6, dx. So we multiply in the minus, and we get x minus x squared plus 6, minus 6 is plus 6. Now we can integrate. The integral of x is a half x squared, the integral of 6 is plus 6x, and the integral of minus x squared is minus a third x cubed. And now we're going to substitute in our limits. So we start with our upper limit 3. We swap each x value for 3, and we get this. Then we have a minus. Then we sub in our lower limit minus 2. We swap each x value for minus 2, and we get this. And we're left with 125 over 6.